All right. Does this work?
Yes, we can see your screen. And we can also see your mouse.
Sorry?
We can also see your mouse.
Fantastic, fantastic. Okay, just two things to say. First of all, that our building is currently renovated, so we are squatting in some much smaller building, and I might be disturbed during my presentation. Apologies if that's going to happen. The other thing to say is that Luyao Zhang, a PhD student working with me, will present a few slides at the end of my time to show some of the things that we've done with the code. Right, so what I am talking about today is using the code called Dusty FARGO-ADSG for disk evolution and planet formation. This is not actually my code. This is a code by Clément Baruteau, but I'll be talking about it from a user perspective, hoping to encourage more people to use it. Right, so a lot of you will know and probably have used one of the Fargo codes. So the original Fargo code was developed by Frédéric Masset more than 20 years ago. It then has been updated in 2016 to be either 2D or 3D. Also, you can use either MPI parallelization or GPU parallelization. There are multiple species of dust that you can include in the simulations. The dust is treated as separate fluids. There's also MHD in this code. So these are all, clear strengths of the code. It's been very widely used and is still widely used in the community. However, there are some disadvantages depending on what exactly you want to do. So, for example, in my group, we are interested in star and planet formation by gravitational instability. The original Fargo code or Fargo 3D do not include disk self-gravity, so you can't address it with the code. There are only very simplistic equation, energy equation treatment included. The gas is either isothermal or adiabatic, there's no cooling. And finally, the code is no longer maintained or updated by the code developers. So you might find it hard to proceed with it if you have a problem. So Dusty FARGO-ADSG is a 2D code that has been developed by Clément Baruteau from the original Fargo code. It is still maintained by Clément. And in my opinion, this is the biggest advantage of the code because Clément is very nice. He provides very nice support for users. That has been my personal experience, and I encourage you to reach out to Clément, and he'll provide you with the latest version of the code. So compared to the original Fargo or Fargo 3D codes, the advantages are that of Fargo ADSG is that the full viscous stress tensor is included in the energy equation. There is a radiative cooling approximation for disks. There's also in-plane radiative transfer. Since it's a 2D code, the radiation is assumed to be transferred by radiative diffusion only in the in the plane of a disk, and vertically there's, as I said, an approximation for radiative diffusion. There's a gas self-gravity included, and there's also a dust treatment. So it could either be treated as a fluid or individual Lagrangian particles. Lagrangian stands here for the fact that in Lagrangian hydrodynamics, the information is carried with the particles. So these are actual physical particles that represent dust particles in your disk. And you can actually use both the fluid and the Lagrangian particles in the same simulation if you wanted to. So that's an interesting feature of code. Now, there are also some deficiencies compared to the original Fargo and Fargo 3D. So the parallelization is only MPI. There's no GPU parallelization. As I mentioned, it's 2D. It's not, 3D. Dust treated as fluid can only be 1 grain size at a time. The Lagrangian dust can have a distribution of sizes, but not the dust fluid. There's also no MHD included in this code. So, you've got to select the right problem or rather the right code for your problem. But there are problems in which the FARGO-ADSG is really fantastic. So from a user perspective, I found that the code is a pleasure to work with. It's written in C with very clear syntax that is easy to understand. It's quite well commented and logically set up. Also, the a problem setup file is very easy to read, and with the same problem setup file, you can then address many problems. Well, commenting or uncommenting different options, you can simulate very, very different problems. There's also a Python utility to analyze and plot the results, which is very nice. So it took me really a day or so to hit the ground running when I started learning the code. And also because the code is easy to understand, it is relatively easy to modify and port additional physics that you need. So now I'm just going to have a few slides on a few applications that we have done with the code. This is an example of a project that we published a couple of years ago, led by Ian Hao Wu, who is a PhD student here, but he's already had his Viva, and now he started a job in Shanghai Observatory. What we've done here is we've done simulations of gaseous disks with dust and embedded planets. We've applied it to a HD 163296 type disk. The interesting thing about this system is that it obviously has dust, and Alma sees it in continuum, and it probably has at least one massive planet because it has a beautiful gap. So what you can do with it is try to use the dynamics of the planet and the dust to try and put some constraints on the mass of a disk. This is usually very difficult, of course, because we don't see hydrogen directly, right? H2 in those disks. But by using the opposite behavior of the planets and dust with the disk mass, you can actually put a lower and upper limit on the mass of the disk. So you might want to read the paper if you want to know more about that. We've also started looking into simulating the very inner regions of these disks, very close to the star at distances of 0.1 AU or so. At high accretion rates, the disk can be so hot that you get hydrogen to be ionized, and that can give you accretion outbursts. They are FU-Ori-like in amplitude, but very short. So I found that I couldn't get the original Fargo to work with this due to the inner boundary condition difficulties, but FARGO-ADSG appears to work. This is not yet published, but promising. Another project we've tried we now have 2 papers submitted, is on the free-floating planets. I am running short, so I'm just going to tell you the highlights here. That what's interesting is that the observations seem to show many bound microlensing planets, shown here in blue, and then an even larger population of free-floating planets. The free-floating planets here means that in the same event, there is no signature of a star. However, that could be that it's either truly unbound or it's just a planet at a wide separation as shown on this plot. And then it's interesting that the population synthesis with core accretion has significant difficulties producing such planets at these wide separations, but GI probably is the answer here. Now, the model that we propose for this is based on simulations similar to some old simulations by Edward, where you've got many clumps, and one of these clumps grows by accretion and mergers into a star. So here is a diagram of what happens in that case. And then from very well known work by Holman and Wigert, we know that that produces a wide zone from which planets can be ejected by the secondary. And in this situation especially, the disk evolves so rapidly that this secondary migrates in faster than the planets, and it rams them and in fact ejects them. So we've checked this now with 3D SPH code Phantom, FARGO-ADSG. These are the snapshots from this paper here with FARGO-ADSG. As I said, this is submitted. We're waiting for a report back. And we find a very high ejection fraction for the planets. So I better stop here and let Luyao to show a few more applications. So I'm going to stop sharing the screen then.
Hello, can you hear me?
I can.
Yeah. Sorry, I can't turn on the camera. I don't know why, but I don't know why I can't share the screen. So sorry.
Sorry, my mic was off. I mean, if Luyao has difficulties with technology, I can just mention what we've done then in words. Would that be okay? Oh,
See my screen?
Sorry.
Okay, I'm so sorry, but I will start. Hello everyone, I'm Luyao, a second-year PhD student. My supervisor is Sergei. Today I'd like to share my work about tracing clumps in GI disks. For the tracing clumps method, I started by identifying clumps at a single snapshot. First, I use a tumor parameter criterion of Q less than 0.1. This is first cut to pick out the GI areas. But not everything unstable is a clump. Self-gravity makes clumps nearly round, so we don't want to mistake irregular structures for clumps, like the spiral arms in this right box. To filter clumps by their shapes, I use the shape ratio, which is simply the arc length divided by the radial extent. Clumps usually fall in the range 0.3 to 3. After applying both criteria, we get the real clumps like this inside the green circle. To trace clumps over time, I use Lagrangian particles as tracers. They are set to small grain size of 1 micron, so they follow clumps dynamics closely. They are passive tracers, meaning that they don't affect the gas. This approach is very efficient in FARGO-ADSG since particle calculations run in parallel. To improve further, I scatter particles proportional to gas density, which reduce their total number while keeping tracing efficient. To link clumps between snapshots, I use a particle overlap condition. For each clump, I define a clump radius as a smaller value of 1.5 Hill radius or 0.2 times its orbital radius and collect all particles inside. Then, for each clump in the new snapshot, I compare it with clumps from the previous one. If they share more than half their particles, they are treated as the same clump. In cases of splitting or merging, I select the most massive match. If no match is found, the clump is assigned as a new clump. As a result, I create a movie showing their evolution over time, with each clump labeled by index. The background is the gas tumor parameter field, and the white central region marks the inner boundary, including the star. At first, many clumps will form along spiral arms and begin to interact dynamically. Clump 2 continues to merge with other clumps and staying near the inner disk. Finally, it merges with clump 12. This movie shows that our tracing method works well, as the clumps are labeled smoothly. It also captures dynamical behaviors. On the left, we see the mass distance relationship. Blue dots mark initial clump states, and the red dots are their final states. Most clumps form at a few Jupiter masses, but clump 2 grew up to about 0.3 solar masses after merging with clump 12. This sudden massive merger is particularly exciting since it may actually trigger an outburst, something we are working now. Our project explores FU-Orion outburst in growing binary systems. FU-Orion outburst is a dramatically brightening event observed in some young stars. Previous studies, like those by Vorobyev, suggested that clump accretion onto the primary star could trigger such outburst, as rapid inflow drives intense accretion. In our work, inspired by clump-clump big merger, we simulated a smaller process, and we inject a Jupiter mass accretion secondary in clump 2 and an Earth mass planet in clump 12. In some cases, like in this animation, a clump merger can trigger a powerful outburst from the secondary star. This provides an interesting new perspective and may offer an additional explanation for FU-Orion outburst. Thank you for listening. Sergei and I are looking forward to your questions.
Yeah, thank you very much for the presentation. Indeed, I can confirm Clément is a very nice person and he answers to emails. So you should feel free to contact him about Fargo, the Dusty Fargo version. The talk is open to questions. Yeah, Eduard, please.
Sergey, Thank you. Very nice introduction in this code. You briefly mentioned a problem with the inner boundary in the original Fargo. Could you say a few words on that? What was that sort of problem?
It's obviously not a problem for the applications that people used the original Fargo, previously, right? Probably 100 papers was published, and they were fine. But for Fury type outbursts, when the temperature of the gas can go up to 30,000 K or so on the inner boundary, it may vary by a factor of 30 easily. And on a very short time scale. So what we found is that we couldn't get the code kept crashing. We couldn't get the time stepping scheme to work correctly.
But why do you think it's the inner boundary? It may be something else, right?
Well, no, it was the inner boundary because
in the inner boundary there to just set the problem. Okay.
Well, it's the inner boundaries where the disk is the hottest, and
what sort of the inner boundary? Is it wave damping, or what they do? They artificially smooth waves in the inner boundary, or it's a free inflow boundary? What sort of?
It depends on the problem. So for many applications in which you have a planet embedded in the disk, you do want to have a wave killing, and that's your typical boundary condition in both original Fargo and FARGO-ADSG. But what we've done for the outbursts was the open boundary condition, and some previous offers have done that as well. That's why we picked it.
Because you need a smooth inflow, right? Flow through the sink to reproduce the burst itself. If you do that wave damping, you may artificially distort basically the light curve and everything. Okay, good. Thanks.
Thank you. Are there any other questions? It's another question from Eduard.
Sorry, I am confused with this.
No problem.
Buttons. All right.
Could you quickly clarify something about the runtime with the Dusty Fargo? Because I assume since it's treated as an extra fluid, if you include the particles, the runtime just doubles, but there's not more penalty than that, right?
So sorry. So you're talking about simulations with Lagrangian particles when you. So that obviously depends on how many particles you use. Clemon usually uses 10 to the 5 or so particles, but it depends on the problem. I believe Luyao has so far used a bit fewer, right? Luyao, could you comment on that?
Yes, I just used 20,000. And I can share screen. You can see it's an efficiency test for the Lagrangian particles, and we can see that because it can run in parallel, so there are many Lagrangian particles, or there are just gas, and there is not that a big difference between these two running time.
Cool.
Yeah.
Thank you very much.
Thank you.
Then, if there are no other questions, I think we should thank Sergei and Luyao again.